Okay, let's start. As you know, there was one homework in the last week. So today we will briefly review this homework. Okay, so the due date was the last week. So almost everyone submitted this homework well. So thank you very much for taking your time to do this homework. I strongly believe this homework will help you to understand what we've done in these courses and then what we will do next in the further lectures. Okay, so today I will briefly solve this kind of homework in the selected number, something like this. Actually, I manually selected those kinds of numbers, but every those problems are very fundamental and important. So if you're not solve this problem yourself, please solve this problem again yourself and try to understand how these kinds of concepts are related to each other. Okay, so let me start. First of all, in chapter 1.1, the topic was the systems of linear equations. So the problem 12, in problem 12, the question was to solve the linear system, something like that. Then how many equations here? How many equations are here? 3 equations, right? Then how many variables are here? 3 variables, right? Okay, then how can I solve this? How can I solve this problem? Okay, first of all, we have to find the augmented matrix of this linear system, right? So 1, 3, -4, -3, -7, 6, 4, 7, -1, -4, -8, 7, something like that, right? So to solve this problem, we have to low reduce this augmented matrix. So first of all, we have to eliminate this one and this one, right? Then how can we do that? How can we do that? Okay, let's say this is a row 1 and row 2. Then by row 2, replacing original row 2 by row 2 minus 3 times row 1, something like that, right? So in this case, this new row 2 will be the -3 times 3 times -3, right? So it will be the 9. So this term will be the 2, like that, right? So similarly, this term 7 minus 3 times 4, so it will be the 12. So it will be the -5, something like that. And this term will be the 4. I will skip the every procedure. So, but please try to solve this term yourself. Then check your solution is right or not. Okay. Then they'll still let's use that. Then from here, okay, let's use a different color. R3 will be the R3 negative what? Negative 4, right? Or just the plus 4, right? Then in here 6 plus 4 times -3, right? So it will be the -12. So it's going to be the -6, something like that. This term is 15 and this term is 19, right? Okay, so what will be next? We also have to remove this term, right? Then Then okay, let's rewrite. Negative 4, negative 4, 0, 2, negative 5, 4, negative 6, 15, negative 9. Then, okay. Then, how can we do that? Using this law to eliminate this term, right? Then, you finally get the minus 4, 0, 0, 0, 7. 3. Okay, so please try to derive those kinds of the procedure yourself. Okay, then as you can see here, in the last row, this law makes some solution like x 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 3, right? Then what kind of solution satisfy this one? What kind of solution satisfy this one? No, right? There's no solution that satisfies this one. So in this case, the solution set is empty, right? Or there's no solution case. Okay, so okay, let's move on to the next problem. Okay, in this problem, determine the value h such that the matrix is augmented matrix of the consistence of linear system. Consistence of linear system. So what is the consistence? What is the consistent? It is related to the existence, right? Existence of solution, right? Then, okay. To determine the existence of solution, let's low reduce this original augmented matrix, right? So how can we do that? How can we do that? Use this first law to remove this term, right? So I will skip from now on I will skip this term. So but you try to imagine those kinds of operation each step, okay? In each step. Okay, so by using this solution, we can find the echelon form of this original augmented matrix, like the 8, 4, 6, negative, 3h, and negative 4, right? Okay, so in this case, okay, let's say this is the constancy, right? Then if c is equal to 0, in other words, h is equal to 2, right? This is the exactly same, right? Then this last row make 0, 0, negative 4, right? Then there is no solution that satisfies this equation. So in this case, when h is equal to 2, there is no solution. Otherwise, h is not equal to 2, then what? The system has a solution. Okay, let's move on to another problem. Okay, this is the row reduction and echelon form section, right? In chapter 1.2. Then problem was the row reduce the matrix to reduce the echelon form and circle the pivot position in the final matrix, in the original matrix, and list the pivot column. Okay, so the problem was to circle the pivot position or find the pivot position and list the pivot column, right? Then okay, so let's do the row reduce first. Okay, So 1, 2, 3, 4, 4, 5, 6, 7, 6, 7, 8, 9, right? Okay, so first of all, remove this one, right? Okay, so and 0, negative 3, negative 6, negative 9, negative 10, negative 12. Okay, then what can we do next? Remove this part. Okay, then 1, 2, 3, 4, 0, 0. By the way, to remove this one, we can first normalize this row, right, as a 1, because if we have the 1 in pivot position, it helps to eliminate this term efficiently or effectively. Okay, so okay, let's normalize this term first, this row first. So you'll be the 2, 3, and they'll still 5, 10, 50, right? And then let's remove this term, right? Then it will be something like 1, 2, 3, 4, 1, 0, 2, 3, something like 2, 2, 1, 0, 0, 0, and 0. Okay. Okay. So to get the problem was the find the reduced echelon form, right? REF form. So we have to remove this term again. So finally, it will be then how can we eliminate this one? By using this rule, right? Then how can you do that? 0, 0, 1, 0, 0, 0, 2, 3. Then new row 1 will be the row 1 times 2 minus 2 times R2, something like that. Then finally it will be the negative 1 and negative 2, right? Okay, so this is the reduced echelon form. Okay, this is the reduced echelon form, right? Then first of all, what is the pivot position? What is the pivot position? Here and here, right? Then what is the pivot column? This one and this one, right? So column 1 and column 2 are pivot position, pivot column, and this one and this one and this one is pivot position, right? So in the original matrix, this one and this one is the pivot position. Okay. Okay, let's move on. Suppose each matrix represents the augmented matrix for the systems of linear equation. In each case, determine if the system consistent related to this is related to the existence, solution existence, right? Then if the system is consistent, determine solution is uniqueness. Solution is unique. Okay, so these two questions is very important question when we analyze the system, linear system, right? Then okay, let's see. First of all, in case A, the shape of the solution, shape of the original augmented matrix looks like that, right? There is a 3 pivot position here with some arbitrary values here, right? So first of all, to answer this question, we have to see the our previous lecture, right? So let's see the lecture 2. Okay, this is the lecture 2 slide. In the lecture 2, there is the uniqueness and existence and uniqueness theorem, right? So to recap, the linear system is consistent if rightmost columns of the augmented matrix is not pivot position. In other words, if the echelon form of the augmented matrix has no rows form such that 0, 0, 0, 0, 0, 0 with t when t is not equal to 0. What does it mean? What does it mean? Something like this. Let's see this one. this row. Okay. If this one is value b not 0, then this row make something like 0 times x3 is equal to b, right? So in this case, there is no solution, right? So this is an inconsistent system, but in this case, this is 0, right? So in this case, this is 0. So in this case, there is no row like this one. So we can say that this solution consistent, right? Okay. Then if the system is consistent, there is two cases: unique solution or the infinite main solution, right? If we go back to our lecture, yeah. If the system is consistent, the solution is the unique solution or the infinite main solution when there is no pre-variable. When there is no pre-variable, there is a unique solution. And if there is at least one pre-variable, there is infinitely many solutions. Why? We can represent our solution set using the using parametric form, right? Then in the parametric formulation, if there is a free variable, as bearing the free variable, we can generate the infinitely many solution, right? So in this case, okay, let's see the this case, x1, x2, x3, and there is a 3 pivot position, right? The number of the pivot position are same as the number of columns or number of the variable. So it means that here, as you can see here, there is no pre-variable, right? In this case, there is no pre-variable. So in this case, we can say that there is the unique solution, right? What about the B? What about the matrix B, right? As you can see here, there is the row like this one, right? Like this one. So here there is a row of the form 0, 0, 0, 0, B like that. So in this case, this is the what? Inconsistent, or there's no solution, right? Then we cannot determine the solution if solution is unique or not. Okay, so this is the problem 15. Okay, let's move on to the vectorization chapter. The question was yeah. Okay, so write the vectorization that is equivalent to the given system of equation, right? What is the vectorization? Something like the x1 plus v1 through the x2, v2 plus x3, v3, something like that, right? With the arbitrary vector b, right? Right there. Then let's do that. Okay. First of all, let's make this equation in a matrix form, like 4x3. Okay. 4x1, x2, 3x3, x1, that was x2, x3, like x1, 6x2 minus 5x3, right? Then we can use this one as a new vector, like the for x1 just 8x1, right? And we can find the term related to x2, then make new column vector like the x2, 7x2, 6x2, right? Finally, the 3x3, 2x3, something like the minus 5x3, right? So this is the 9 to 15, right? Then from this one, oh, by the way, this is the x1, right? From this one, we can extract the x1 from this column vector, so it will be like this one, right? And another thing is that x2 will be the 7, 6, right? And will be the x3 times 30, negative 2, negative 5. Done? Okay, try that. Okay, so in this case, this vector is then v2 is this one, v3 is this one, b is same as the original matrix form. Okay. Okay, so let's move on to another problem. Okay, let's say v1 is equal to 1, 0, negative 2, v2 is something like that, and vector y is something like that. For what values of the h is y in the plane generated by v1 and v2? Okay, so first of all, what's the meaning of the plane generated by v1 and v2? What is that? This is the span, right? The definition of the span, right? Then so it means that to this value, okay, let's write like that. Okay, so the system x1 vector v1 through the x2 v2, right, with the vector y, something like that, and this vector y is in the plane generated by v1 and v2 when there is a solution x1 and x2, right? So because this is the definition of the span, right? So in other words, this problem is equivalent to the finding the solution, or the analyze the existence of solution of this equation. Okay, so to solve this one, let's make the matrix equation something like v1 v2 with the x1 x2 something like vector y, right? Then to solve this one, we can make the augmented matrix something like that, right? Then it's negative 3 1 8 h negative 5 3 like that. Then we can row reduce to easily, right? Then how can we do that? Negative 3 h 0 1 negative 5 0 2 minus 3 plus 2h. Why? Because we want to remove this term using this one, right? Then we can remove this term, right? Again, right? Using the 0 negative 3 h 0 1 negative 5 0 0 2 7 plus 2h. Okay. So to determine the solution is exists or not, we have to think about this term, right? if you remember this one, this p, if this p is not equal to 0, there's no solution, right? But if p is equal to 0, there's a solution, right? So it means that if h is 0, say that h is negative 7.2. In this case, there's a solution of this equation, right? So it means that there exists some value x1 and x2 that satisfy this equation. So it means that this vector y is in the plane generated by v1 and v2. Okay. So let's move on to the next chapter. The chapter 1.4 was the matrix equation A is equals B, right? So given, where is that? Yeah. So, okay, the problem 11 is that given matrix A and B, write the augmented matrix for the linear system that corresponds to the matrix equation A equals B, then solve the system and write the solution as a vector. Okay, so what was that? What is the augmented matrix of this one? 1, 2, 4, 0, 1, 5, negative 2. Negative 2, negative 4, negative 3, negative 2, 2, 9, right? Okay, let's slow reduce this one, right? 2, 4, negative 2, 0, 1, 5, 2, and 5, because we use this law to remove this one, so it means that row 3 will be the row 3 plus 3, 2 times row 1, right? So it will be the 0, 5, 5, right? Then 1, 2, 4, 2, 0, 4, 5, 2, 0, 0, 1, 1, right? Okay, we found the ones on the diagonal. Then what do we do next? We have to remove this one, right? By using this one and this one, or this row and this row, right? Then finally, please try to solve this yourself, okay? So I strongly believe you already done this, right? Then it will be the something like that, right? So in this case, this one is related to x1, x2, x3, right? So in other words, x3 equals to 1, x2 is equal to what? Negative 3, x1 is equal to what? 0, right? So final solution vector x1, x2, x3 is going to be what? 0, negative 3, 1. Okay, so let's move on. This is problem 18. Okay, so do the columns of the matrix B span the R4 space, and does the equation B times x is equal to y have a solution for the vector y in R4 space? Okay, this is the problem. Okay, to answer this problem, we need a theorem in the lecture 3.1. Okay, so if we go back to the lecture 3.1, there is the theorem, something like that, right? Okay, so this solution said that for each p in the Rm space, the equation A equals B has the solution, and each p in Rm space, the linear combination of the columns of A and the columns of the matrix A span Rm space, and A has a pivot position in every row, right? So all these four statements are equivalent. So it means that for particular A, either they are all true statement or they are all false statement, right? Okay, so if we go back to our problem, the columns of B span R4 space. R4 space is the equivalent to the Px is equal to y have a solution. So these two questions is equivalent. Okay. So to answer this, we can analyze this matrix B by using any kind of statement here and here and here and here. So any statement can be used to analyze this matrix B. Okay. In this case, let's use this one. If A has a pivot position in every row, columns of matrix A span the Rm space, and the equation Ax equals B has a solution. Okay. So first of all, how can I find the pivot position in matrix B? How can I do that? How can I do that? We have to row reduce, right? We have to row reduce. Okay. First of all, remove this one, right? Right. Then 1 negative 5 0 0 0 0 0 0 0 negative 7, right? If we interchange row 3 and row 4, then final echelon form of the matrix something like something like that, right? Okay, so where's the pivot? Where's the pivot position? Here, 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 right? So there is the four columns, but there is a three pivot position, right? Right. So it means that in here, A has a pivot position in every row. Okay, let's say this is the full rows, right? Full rows, and each row, these three rows have the pivot position, but this row doesn't have the pivot position, right? So in this case, we can say that this is not true, right? So in other words, what? Equation P x is equal to y does not have the solution or no solution, right? And the columns will be is not span the alpha space, okay? Columns will be not span R4, okay, because of this theorem, okay? Okay, so let's move on. In the chapter 1.5, the solution set of the linear system, there is a problem. First one is suppose the solution set of the certain system of linear equation can be described as x1 blah 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 blah, something like that, with the x4 is free variable. Use the vectors to describe this set of the set as a line in the R4 space. Okay, so let's do that. Okay, so first of all, let's write the vector x as a x1, x2, x3, and x4, right? Then what is x1? 3x4, a plus x4, right? 2 minus 5x4, right? And x4, because x4 is a free variable, right? Then let's decompose the constant term 0, 8, 2, 0 with the x4 term, like 3x4, x4, right? Negative 5x4, x4, right? Then we can extract x4 from this column vector, right? Then it will be like x4 is going to be times 3, 1, negative 5, 1, right? So in this case, we can say that this is vector p and this is vector q. Then the final solution will be the x4 times this one. Okay, so in this case, x4 is the scalar value, right? So we can say that the solution set x is the line through vector p in the direction of q. Okay, so if you remember the chapter 1.5, so you can imagine the shape of this line, right? So in the 2D or 3D space, but in this case, because this is a 4D vector, so or the R4 vector, so it's not possible to draw. So, but we can say that this is a line through the vector p in the direction of the vector q. So please, if you are not understand this statement, please go back to the 2D or 3D case in our slide and then think about what this meaning. Okay. Okay. So yeah, here's a true or false question. True or false question and justify the answer. Okay. So first of all, homogeneous equation is always consistent. True or not? True. Why? So, homogeneous system Ax equals B has at least one solution as a trivial solution with x is equal to 0, right? So this is true. And then the equation Ax equals B has a trivial solution if and only if the equation has at least one free variable. If and only if the equation has at least one free variable. True or not? Oh, wait. Ah, there's an error here. This is not the problem in the problem 23. So the original problem was, okay, let me check. Where is that? Yeah. 1.5, where is oh. The original problem was the equation Ax equals B gives an explicit solution. Explicit description. of each solution. Okay, so this is a question, but actually this is first. Actually, the explicit solution was the solution something like the what's that? So let's see the text. Yeah, the explicit solution looks something like x is equal to su plus t v, something like that. So, and in C, So in C, the homogeneous equation A equals 0 has a trivial solution. If and only if the equation has at least one free variable. What does it mean? So equation has the at least free variable means what? It has an infinite remaining solution, right? So this means infinite remaining solution. Right? So if there's infinite remaining solution, A equals 0 has a trivial solution, right? So this statement are true, but when you think about this one, if A equals has a trivial solution, the equation has there's two cases. There is a one solution case. There is an infinite remaining solution case. So we cannot say this trivial solution guaranteed the infinitely many solution, right? So in this case, this statement first, okay. And the equation x is equal to p plus tv describe the line through the v parallel to p. This statement first. Why? It should be p v, right? Because there is p, there is v, right? And the solution set of the ax equals b is the set of the all vectors of the form y is equal to p plus vh, where vh is any solution of the equation a is equal to p, right? So in other words, this solution set is the vector p plus the solution set of the homogeneous system, right? So this is first or not? First. Why? To this statement is true, the solution p that satisfies this one should be exist. If not, we cannot say the solution W is equal to P plus VH. So if not, we can this solution set could be empty or no exist. So this statement are true first. Okay. And then chapter 1.7 is the linear independence. Then how many pivot positions of the how many pivot columns what was that? Yeah, let's do that. 7 27, right? How many pivot columns must 7 by 5 matrix have if each column if each columns are linearly dependent, and why? Okay, so this is the question. Okay, so if each columns are linearly independent, what does it mean? If these columns have a linearly independent, then what is the linear independence? Let's go back to the what was that lecture? What was the linear independence? Do you remember? Lecture 3.2, right? Yeah, here. No. Where's that? There it is. Okay, let's go back to the. Okay. So, what is the meaning of the linear independence? Linear independence. There should be what? If we represent this matrix A with the solution vector x in a homogeneous system, then if there is a solution that is not x equals 0, it means that non-trivial solution, then we can say that ax equals 0 has a non-trivial solution, right? Then in this case, it means that the columns of the vector A has the columns of vector A linearly dependent, right? So what does it mean? Okay, let's say there is a matrix A, numbers row 7 and number of columns of 5, right? Then okay. There is the 5 variable, right? And if every column has the pivot position, something like that, then there is no free variable, right? In this case, there is only trivial solution as x equals 0, right? So in this case, it will be the linear independence. Linear independence. Okay, let's say the columns of the matrix A is the columns of the matrix A are linearly independent in this case, right? So how many pivot columns must in here? In this case, 5, right? If not, x equals 0 has the infinitely many solutions, so the columns of matrix A would be linearly dependent, not independent. Okay. So let's move to the next problem. Okay, so give the matrix A something like this. Observe that third column, this one, is the sum of the first one and second one. Then find the solution of the A equals B. Okay, let's think about that. Let's say this is the set of the column vector like that. In here, in this statement, we already know the A3 is A1 plus A2, right? Then we can say that A1 plus A2 minus A3 is equal to 0, right? Then because this is a column vector of the matrix A, right? Then we can represent this matrix A with the solution coefficient here 1 1 negative 1, right? So it will be the 1 1 negative 1 like that, right? With the 0, right? So trivial solution of the matrix AX is equal to 0 is the X vector 1 1 negative 1. Okay. Okay. So let's move on. Okay. So the problem 20. Yeah. Let's say there is X vector X and V1 and V2, and let's say the transformation T R2 from R2 be a linear transformation that map the input vector X into the X1 times V1 plus X2 times V2. Find the matrix A such that the transformation X is the AX for each X. Okay, so first of all, what should we do? Okay, let's write the Tx. X. Then transformation Tx is mapped this original X to the X1 V1 plus X2 V2, something like that, right? So we can represent this vector V with the X1 and X2, right? Right, like that. What was that V1 and V2? It was the minus 2, 5, 7, negative 3, something like that, right? With the vector X, right? So finally, this is the matrix A. So in other words, matrix A is going to be negative 2, 7, 5, and negative 3, right there. Okay. Okay, so there's one more problem. Okay, so on affine transformation, let's say this is affine transformation. T Rn for Rn to the Rm has the form Tx is the Ax plus B with A matrix A is a n by n matrix and B is in Rm space, and show that the T is non-linear transformation. Okay, so when P is not equal to 0, okay, then how can we do that? How can we do that? So to determine this linear transformation is this transformation is linear transformation or not, we have to check the properties of the linear system, a linear transformation, right? So what was the property of the linear transformation? What was that? What was that? Transformation Cx is equal to C transformation X, and transformation X plus Y is equal to X plus X transformation X plus Y. Okay, so you have to check the this transformation satisfy these two properties. Okay, so from this equation you can derive this left hand side and right hand side and check if they are same or not, and you have to derive this one and this one and this one and check they are same or not. Okay, so this is the what you can do to determine the linear transformation or not. Okay, this is a final problem. So this problem, the linear transformation T R2 to R2 be the linear transformation such that transformation elementary vector E1, right? So this is the 1 0, right? This is 0 1, something like that, right? So transformation E2 are vector in the figure. Let's say TE1 is something like this, TE2 something like that. Using these figures, catch the vector T21. Okay. So first of all, let's represent the vector 2 1 as a 2E1 plus E2, right? By definition, right? Then what is the transformation 2 1? Because this is a linear transformation, then you'll be the TE1 plus TE2, right? TE1 here, TE2 is here, right? Then by parallelogram scheme, we can draw the T 2 transpose E1, then